Here, in this talk, I'm going to talk about my current investigations on superstructures in thermal convection far from the onset. So I'll just explain superstructures as Professor Stevens talked recently about superstructures. We also study superstructures, but we don't focus on Nusselt and Reynolds number scaling, but we measure their characteristic scales and how these length scale vary as function of Prandtl numbers. So we focus more on Prandtl number dependence and not on the aspect ratio. So I'd like to just give a outline of my talk. So I'll introduce my research with some motivation, then I'll introduce briefly about equations and simulation details. Then in my results, I will discuss about the profiles of heat and momentum transport, profiles and global transport of heat and momentum. Then I'll discuss about these superstructures, how do we detect them, and we also observe some defects in our patterns in large aspect ratio boxes. Then I'll conclude my talk with some outlook. So first I'll just introduce my system. So to motivate the thermal convection, which is driven by buoyancy, is in last 4 days we have seen many lectures on this. So it is crucial in many places in nature. So for example, in sun, in outermost part of sun, this is main mode of heat transport. Here I would like to point that Rayleigh number, which is measure of destabilizing buoyancy force, is extremely high and Prandtl number is extremely low. So flow is highly turbulent here, extremely turbulent. Still we see patterns, regular patterns. So these patterns are called granules, whose typical size is about 1,000 kilometers. There are bigger patterns too, with known as supergranules. So in these extreme situations, patterns are there. Another example comes from the atmosphere. So this is a real satellite image of cloud streets over Bering Sea. So when cold wind comes from snowy region over the hot water or sea, it climbs, and on top of it, cloud patterns are formed. So here the clouds are formed in like parallel rows. So white patterns are cloud and dark patterns, dark structures, they are clear sea. So again, Rayleigh number is 10 to 18, extremely high turbulent flow here. Prandtl number is moderate, 0.7, but still regular patterns are there. So we would like to understand where these patterns are coming. So some questions are arising. So these patterns means in these systems, one thing is there that horizontal extent is very high compared to vertical extent. So they are large aspect ratio systems, and regular patterns are formed in turbulent convective regime. So questions are, where do these structures come from? Are they related to the structures present near the onset of convection? So near the onset, some structures appear. And what is their statistical impact? So as Professor Stevens talked, that how do they contribute to Nusselt number, Reynolds number scaling? So to answer, so one more thing, that in those systems which I showed for motivation, they are not just driven by buoyancy or thermal gradient. For example, in sun, magnetic field is present, rotation is present in atmosphere. These effects are present. So, but we would like to answer these questions by studying some simple phenomena, which is Rayleigh-Benard convection. So in which fluid is placed between a hot bottom and cold top plate, and when temperature difference reaches a critical value, convective motion starts taking place in the system. So heat and momentum transport depends on temperature difference, and in addition, they also depend on the properties of fluid. So we focus on extended systems in which patterns are formed near the onset of convection. I will show one example, but these patterns disappear due to increasing turbulent fluctuations if we increase Rayleigh number or temperature difference. So, but to again get these patterns or look at these patterns, we need to remove these fluctuations by either time averaging or by spectral filtering, these kinds of things. Then we can get large connecting structures. These are known as turbulent superstructures in the context of Rayleigh-Benard convection. So in this talk, I'm going to discuss how the characteristic scales and dynamics of these patterns we have as function of Prandtl number numerically. So to solve, to study this system numerically, we need to solve governing equations of the system of Rayleigh-Benard convections, and these are the governing equations. So momentum equation, heat equation, energy equation, and mass balance is there, continuity equation. Some important non-dimensional parameters which govern the dynamics of RBC are the Rayleigh number, which is proportional to temperature difference in the system. Prandtl number is ratio of kinematic viscosity and thermal diffusivity of the fluid. So for higher Prandtl number fluid, your heat is, your momentum is diffused quickly compared to heat. And so we study as function of Prandtl number, that's why I'm emphasizing the Prandtl number dependence. And aspect ratio, gamma is aspect ratio. This is ratio of width of the system to the height of the system. So this is our simulation domain. We solve these equations in aspect ratio 25 box. So all the walls are rigid. Professor Stevens presented in periodic boundaries. So here all the walls are rigid, and these two are conducting boundaries, isothermal boundaries, and side walls are insulating boundaries. So no heat can penetrate from the system. So we study three working fluids: mercury, air, and water. At moderate Rayleigh number, we have gone up to 10 to 7, a bit higher Rayleigh number, but I'm not going to discuss that case. Here I'm showing the structures of isosurfaces of product of vertical velocity and temperature field. So these are hot structures going upward. This is just our simulation domain. So we solve these equations using a code NEC 5000 using spectral element method. So we take around 2.3 million elements, and within each element we also refine them using up to 7th order polynomials. So we have huge number of grids. Now I'm going to present some of my results based on our simulation data. So this is standard temperature and velocity profiles in Rayleigh-Benard convection. So if we are in conduction state, temperature varies from bottom to top linearly. But due to presence of fluid motion, this temperature profile modifies, and the temperature difference mainly confines to two thin layers near the top and bottom plates. These are called thermal boundary layers. So here we can see that thermal boundary layer means width of thermal boundary layer is increasing as we decrease Prandtl number. So this red curve is for mercury. So here we can see that thermal turbulence is not, it's not quite turbulent. We still have gradient in the temperature field in the bulk. And for Prandtl 0.7, we have turbulent system, so temperature is approximately constant in the bulk. For Prandtl 7, which represents water, this gradient is positive. So this gradient is positive, means in bulk, temperature is increasing in the top, if we go from bottom to top. So which might be due to plume overshoot, due to mushroom type nature of the plume, but I'm not sure about this. Here I present the RMS horizontal velocity. So horizontal velocity is 0 near the top and at the top and bottom, and as we go to bulk, its strength is increasing, and in bulk it's approximately constant. So as we decrease Prandtl number, velocity magnitude is increasing, which is in line with increasing Reynolds number as function of as we decrease Prandtl number. So we would like to, as I have said, this heat and momentum transport depends on temperature difference and fluid properties. So we quantify them using Nusselt number, which is ratio of heat, total heat transport to the conductive heat transport, and we compute using velocity and temperature field in our simulations. Similarly, Reynolds number we measure using root mean square velocity field, averaged over whole simulation domain. So these, in non-dimensional term, these numbers, Nusselt and Reynolds number, they depend on Prandtl and Rayleigh numbers. And it has been observed that alpha or Rayleigh number, Nusselt number exponent lies between this range, and Reynolds number range lies between this range. Prandtl number dependence has also been measured. So here I'll just show that Nusselt number, because Rayleigh number is 10 to 5 in our case, so Nusselt number increases initially for smaller Prandtl numbers, and then it becomes approximately constant. And Reynolds number is decreasing as we increase Prandtl number. So this was also very clear in profile when velocity magnitudes are increasing as we decrease Prandtl number. So this dashed curve is fit from the model which we made with Professor Verma. He presented in his talk. And these coefficients are functions of Rayleigh and Prandtl number. We can see that this model was made for aspect ratio, means these constants were determined from aspect ratio 1 box, but they also work quite well for aspect ratio 20 box. So they are approximately well, means they match approximately well. These functional dependencies are also consistent with Grossman-Losse theory. So this is Prandtl number actually. This is it depends. For Mercury, we have only one Rayleigh number, but for Prandtl 0.7, it's around root RA 0.7. So now I would like to just discuss about the patterns in our high aspect ratio box. So as I discussed, to get these patterns, we need to remove fluctuations in the turbulent state. So we have several. So to remove fluctuations, we time average our velocity and temperature fields. We also do spectral filtering. So we transform to Fourier space and remove small scale modes, means large wave number modes, and then we transform back and we can get the average structure, but we perform time averaging here. So for time averaging, we have several time scales in convective system. So one is free fall time, so through which the equations are non-dimensionalized. Then we have thermal diffusion time scale, we have viscous diffusion time scale, then plume detachment time scale, which is order of free fall time, then Lagrangian eddy turnover time scale, which is when a Lagrangian particle again crosses a particular point after following the large scale circulations, which is about 10 convective time units. So for example, typical diffusion time scale, one diffusion time scale is related to free fall time unit as this. So one diffusion time unit is about 46 units of free fall time, and it depends on Prandtl and Rayleigh number. So we found that vertical thermal diffusion time scale is appropriate unit for our averaging procedure, and we are going to use this time scale in our subsequent slides. So here, for example, temperature field at mid horizontal plane is shown as Professor Stevens showed recently. So this is at mid height. So red structures are hot structures coming out of the plane. Actually, this is a view from bottom. So these are coming into the plane, and blue structures are coming down. And so here we can see some structures, but they are not very clear. So if we time average for 0.1 diffusion time, you might get some structures, but we are interested in defects. So I will discuss just 2 minutes later what defects are. So to get or to observe defects clearly, we need clear patterns. So then we average for 0.5 eddy turnover time, 0.5 diffusion time. So fluctuations are removed and patterns are getting clear. If we average for longer time, you might lose some information from your system, from your structures. So here, when we perform averaging, this instantaneous snapshot was kept in center. So summary is your averaging should not be too long, otherwise you will lose some information from your pattern, and it should not be too small, otherwise you cannot detect patterns or cannot detect defects. So we find that half thermal diffusion time is appropriate time scale for our system. And in next slides, all the snapshots or movie which I'm going to show are average for half thermal diffusion time. So here, these are velocity streamlines as function of Prandtl number. This is a view from bottom. So these are streamlines, and in this plot, these are streamlines are plotted along with the temperature contours. So gray pattern is hot structures going into the plane, and dark structures, dark contours are cold structures. So hot fluid is going in above, or it's rising through these sides, and cold structures are hitting the cold walls at these sides, the darker sides. So one thing is for notice that the characteristic roll width. So these are rolls, and the roll width is function of Prandtl number. So we want to quantify how this is varying with Prandtl number, and we can see that regular pattern is observed for all the Prandtl numbers. So these are time average for half diffusion time. So to quantify the characteristic length scales, we can use Fourier transform. So for example, velocity field is 0 at the boundaries. So this is kind of periodic in our case, means it is 0. So we take vertical velocity at mid horizontal plane. Here again, this positive velocity is hot structures going up. If we transform it, we find that dominant wave numbers, or they cluster on a circle. Like he showed that spectrum peaks at some particular point, particular wave number. So we can see that the dominant wave numbers, so this is on log scale, they lie on a circle of radius some k, and inverse of that wavelength will give you a characteristic length scale. And if we look at the function as function of Prandtl number, we can see that this circle is getting smaller as function of Prandtl number. So in physical space, characteristic scales grow with increasing Prandtl number. We can again quantify these structures using spatial autocorrelation functions. So we took the field which I showed in last slide, velocity field, and we define correlation functions as this. If we look at the correlation function, they decay, and so the first minimum, which is negative of correlation function, it represents the distance at which hot structures and cold structures are moving upward and downward. So twice this value you can take as the characteristic wavelength of the pattern. So similarly, theta, which is temperature fluctuation field, which Professor Verma explained in his slides. If we look at the theta and compute spatial autocorrelation function, they also behave similarly as UZ. So here we plot first minimum, means twice the first minimum of these correlation functions, which is characteristic wavelength of the pattern, and it increases slightly as we increase Prandtl number. So this is weak increase as function of Prandtl number. Here stars are the stars represent data which they also represent the wavelength we determine from Fourier space. So we determine k, and 2 pi by k will give this star. So we find that characteristic length scale determined from physical space as well as Fourier space are all consistent, and scales grow with increasing Prandtl number. So now we would like to show some patterns and defects in patterns. So defects are defined as irregularities in otherwise regular patterns. So this is a snapshot temperature field near the onset of convection, where critical temperature difference is not much higher, where temperature difference is not much higher compared to critical one. So here pattern is mostly regular in most of the places, but at some locations some discontinuity is occurring. So for example, this is a defect which is called dislocation, where a pair of rolls terminate, stripes. So we also have other kinds of defect: disclination, focus singularity, grain boundaries. So this is near onset, but we also detect dislocation in our system which is far from the onset. So Rayleigh number is 10 to 5. It is quite turbulent, and this snapshot is temperature field for Prandtl number 0.7. So we can also see that when dislocation is here. So we would like to see how these defects move as we progress in time. So in next in this slide, I'm showing movies for this is mid horizontal plane temperature field, and as we are progressing in time, and each snapshot here is averaged for half thermal diffusion time. So defects are clear. For example, these defects are moving. So here you can see that if you focus in this, one defect is here right now, and after some time it will move to here. So defects are moving and patterns are forming. So in all Prandtl numbers, we detect defects, and we are trying to study their dynamics, how these patterns move and how they are related to defects. So here we show that these are snapshots from last slide for Prandtl number 7.7, and at one particular instant, one defect is here. If you move in time, then this defect has been moved and your structure has been changed. So as you move, these patterns are evolving. So we are just studying these patterns. So we have not fully understood this. So we found that these patterns evolve on the order of thermal diffusion time. So this is relevant time scale for our study. So now this is all, and I'm going to summarize my findings. So we study turbulent superstructures in horizontally extended thermal convection far from the onset. So for that, we studied 3 working fluids: mercury, air, and water, at moderate Rayleigh number using direct numerical simulations. We found that Nusselt and Reynolds number, which are heat and momentum transport, they are approximately same as near gamma is equal to 1 or aspect ratio 1 box. We studied time average structures of temperature and velocity field, and these these structures are somewhat similar to those found near the onset of convection. They are not exactly same, but similar. So we determined the characteristic scales in our system in these patterns, and we determined using Fourier, and in physical space, they are all consistent. And typical pattern scale increases, we increase Prandtl number. So we also get defects in these patterns, and we studied their dynamics. So as we progress in time, these defects are annihilated, some are created, and our pattern is moving, a pattern is formed. So we are also continuing our study for higher Rayleigh number. We have already obtained 10 to 7 Rayleigh number data, and we are trying to get more. And we are focusing on lower Prandtl number data, because in Sun and their Prandtl number is extremely small. So we have got data from sodium. We will present in next communications. And in addition, we are also trying to study these superstructures as using Lagrangian tracers. So this part Jörg Schumacher is doing, and in future we will all present these studies. So thank you for your attention. I'm thankful to DFG, Turbulent Superstructure Priority Program, for the funding, and these supercomputing centers for giving us computing network. Thank you for your attention.
It is an excellent talk, clearly showing all these structures, how they evolve, and pointing out defects. If you have any questions, Pankaj, wait.
So in your cross correlation picture, you have very systematic oscillation, and yes, also this oscillation grows.
This one for theta.
Yeah.
Actually, for this one, we have velocity is 0 at all the walls. So finally, when you you are very far, it's 0. So it's 0 at maximum distance, because it's autocorrelation, first of all. So it is 0 at very far. And for theta, it's not correlated. Means they are, so for theta, it's not 0 at the boundaries.
Is it periodic oscillation or?
This is kind of periodic because we have wavelength, horizontal. In horizontal direction, we have up, down, and means in upward moving and downward moving plumes. So they are kind of periodic roles. Their wavelength is there. So that's why we are getting regular period, regular oscillation.
Any other questions?
Yes, it's kind of
Similar, no? That's aspect
here.
4.
Here, yes.
Yes, 4
So
is
scales is
4 to 5.
yeah. So this is aspect ratio 25 only. They have done up to till 128 aspect ratios, but we are focusing more on lower Prandtl number fluids. Yes, yes.
So your structure that you see depends on the time of averaging. In fact, one could argue that since these are just a minute. In fact, one could argue that none of these average structures exists because only structures exist in the instantaneous field.
Yes.
So the type of structure that you see depends on how long you average. In fact, you average over a long period, everything will vanish.
Definitely.
So how do you decide this TD? One has to do that based on finding out the characteristic time scale of your fluctuations. So how did you choose this 0.5 TD?
For example, here we averaged for 4 different windows. We also averaged for 3 diffusive time units. And this is just for Prandtl number 0.7. We also did for mercury and water. And so we found that half thermal diffusion is kind of relevant time scale for all the cases. So it will, relevant means we can detect defects quite clearly. If you look here, what? Visually, yes, yes.
But one should actually find out the PDF of fluctuations versus time.
Okay.
And then find out what is the time scale of your fluctuations and then just remove the fluctuation.
Okay.
Over that average, over that time.
Okay.
But even in that case, these are actually fictitious structures because structures exist only in an instantaneous thing.
Yes.
So what physics would you get from a fictitious structures which are average structures?
So these are averaged, definitely the instantaneous ones exist, but the fluctuations are there about some mean pattern. That is definitely there, which is not, but to look at those mean structures, we need to remove those fluctuations. We have mean state near onset of convection, some time independent state, and due to increasing fluctuation, this is not appearing. But if you remove these fluctuations, they are you can see them. And defects are there, so we are focusing on defects. So to clearly detect a defect, we need a time average patterns.
I do have this similar kind of query what Professor Baburaj has. Perhaps maybe it's quite interesting to see this kind of fine scale details which might have further consequences on heat transport. While averaging out naturally, these fluctuations will smoothen out because of diffusion, whatever it is present. Yes. But nevertheless, it's always nice to find out the information like why these structures are coming out of this turbulent environment.
Yes, so that's our objective, why they are, yes.
Thanks. With the scaling of the widths of the rolls that you get at the onset of convection, are they sort of similar or are they very different?
No, they are not similar. Near onset, they are order of your system height. But as you increase your Rayleigh number, the width is increasing. So at 10 to 7, for maybe for same Prandtl number, we have less number of rolls. So 10 to 7, we have only, maybe here, I have around 6-7 pairs of rolls, but there I'm getting just 5 pairs of rolls. So this width is also a function of Rayleigh number. But since we don't have enough data right now, so I'm not showing this.
Thanks.
Any other queries? If not, let us thank the speaker.